first section of the class concerned oscillations into waves, into superposition and how waves interact with each other in themselves, including standing waves, which moved into light. It seems like we're taking an a massive break right here and a shift in subject matter by going into electric charge. But I hope to make the argument very shortly, well, not very shortly, at the end of the semester, that it's not. That they do eventually all tie together. Now, the electric charge of an object is given as Q, and the units are coulombs C. Now, this is a fundamental, the coulomb is a fundamental unit. And by a fundamental unit, that's one where we just have to pick a scale and say, okay, I define this to be a unit of mass, this to be a unit of length. The other fundamental units that we've run into in the previous semester involved meters, an arbitrary unit of length, kilograms, an arbitrary unit of mass, and seconds, an arbitrary unit of time. Now, if I've got electric charge, now electric charge comes in three flavors. And I could list this as thing one, well, thing two, and thing three, such that if I have, let's look at my different options. Okay, suppose I've got type 1, where I have two objects of type 1, there is no force between them. However, if I have type 1 and type 2, there's an attractive force between those two charged objects. If I have thing 1 and thing 3, there's an attractive force between those two objects. If I have thing 2 and thing 3, then there's a much stronger attractive force between those two objects. But if I have, say, thing 2 and thing 2, or type 3 and type 3, there's a repulsive force between those two objects, then, actually, make this 25.0, then I could say, okay, there must be three different flavors. Flavor 1 doesn't affect the universe at all, but it is attracted to type 2 and type 3, flavor 2 and flavor 3. Flavor 2 and flavor 3 attract each other very strongly, but they repel themselves. It attracts the other, and it attracts thing 1, but it repels itself. Now, for no reason than besides that it makes the math work, which is a darn fine reason in and of itself, I'm going to call thing 1 and speak of that as being charge neutral. Not saying that it has no charge, I'm saying that the net charge is 0. I'm skipping a lot of historical development here and cutting straight to Benjamin Franklin et al. Came up with the idea of thinking, well, maybe charge is made up of a whole bunch of tiny particles that can move about. So, if the net charge is 0, then that'll be flavor 1. and then I pick and I call one of the others positive, and one of the others negative. The reason why I do that is that then, if I use the equation derived by Charles Auguste Coulomb, of whom the units of charge are named, that the electric force of thing 1 on thing 2 is equal to the charge on thing 1 times the charge on thing 2 divided by the distance between them squared, and this should not be coming out of nowhere. Do recall that in chapter 13, the gravitational force between two objects depended on the mass of thing 1 times the mass of thing 2 divided by the distance between them squared. Now, we're using coulombs to represent units of charge. We are choosing whatever units of distance work well for us, say meters. How does the universe know that? It doesn't. So, we need to throw in a constant, k, to account for that. The book uses k, instead of k, it uses something to develop a little bit later, 1 over 4 pi times epsilon naught, where epsilon naught is another constant whose existence was derived by Carl Friedrich Gauss. I'll talk about this when we get to Gauss's law, which we're only going to cover in passing. In fact, I'll cover a brief discussion of Gauss's law on my next movie recording day, next Monday at the very latest. But the reason why I keep this as a constant k is because, if you just put that as k, that comes darn close. It's 8.99. But it comes darn close to just being 9 times 10 to the 9th Newton meters squared per Coulomb squared, which is an easy number to track. In the same way, the force of gravity needed a constant, capital G, to track that. Now, the force of gravity is always attractive, so the direction is always radially inward. R represents a radial vector, a vector going outward from a point. R hat, that carré, means that it's a unit vector, has a length of 1. So it's only telling me a direction, straight out away from where the heck I am. And negative means, flip that around, straight in to where the heck I am. So this then becomes, the electric force of thing 1 on thing 2 is given by a constant k times the charge of thing 1 times the charge of thing 2 divided by the distance between those two squared times the radially outward from this point. Now, the reason why this works is that if I have, like, say, two positive objects, two positive charges, a positive times a positive is positive, I'll get an electric force radially outward or repulsive. If both objects are flavor 3, negative, a negative times a negative is a positive, the net force is positive, the direction then is positive radially outward or repulsive. If one is positive and one is negative, then I've got a positive times a negative or a negative times a positive, which either way is, hey, a negative. And that results in a negative force, which means I have a force that's negative radially out or inward.